Good morning, class. I hope everybody's doing fine. This is section 2.8, the derivative as a function. Okay, so we looked at various sections, and now we are finishing off with 2.8, and it's pretty similar to 2.7, what we have seen. There's really not much brand new. Instead of dealing with differentiation at a specific point, we deal in general with differentiation. So with that being the case, as you recall, when we discussed the differentiation at a specific point, the idea was very simple. We had a slope of a secant line. Okay, basically, that's a secant line, the blue one. And then as we get this blue line closer and closer to the red line, in other words, Q gets closer and closer to P, it becomes the slope of a tangent line. Okay, it becomes a tangent line and a slope of a tangent line. So we have this definition, which is known as rise over run. And then when we take the limit, it becomes a differentiation. And that's really the bottom line. So having said that, we've seen this, there's nothing brand new here. So what we are going to add is that instead of A, we are going to use X. So it's really the same definition. So what happens, it becomes known as the differentiation formula in general, the derivative function, the derivative function. So that's what it becomes. So having said that, let's look at various notations that are used in differentiation. Now, I quickly go over them. F prime of X, Y prime, dy dx, df dx, d dx of f of x, capital D f of x, capital D sub x f of x. Those are called differentiation operators. Normally, we use the first three, class. I'm not saying that those are the only ones, but normally we use them. Now, going back to this formula, what is delta y over delta x? Rise over run. Rise over run, the slope of a secant line, in essence. If you let delta x go to 0 and you take a limit, now we call it dy dx, dy dx. A function is considered differentiable at a if f prime of a exists. It is differentiable at open interval if it's differentiable at every point, every number in that interval, okay? So having said that, let's repeat the question we have seen in the previous section, finding an equation of a tangent line, nothing brand new, okay? The difference is, instead of differentiation at a, and a is 8, by the way, if we were to go with the previous section, but let's this time take it at x, okay, class? So keep it at x. So we are going to put it into this limit formula, and as long as we can put it into this limit formula, practically we're done. So you replace the x with x plus h. So now we have the limit as h approaches 0 of 3 times x plus h plus 1 under the radical, minus the square root of 3x plus 1 over h. Okay? As you can see, this is 0 over 0. And so when it's 0 over 0, we have to use our algebraic techniques to fix the problem. So what algebraic technique do you think we need for this question, class? Anybody? What algebraic technique will do the job for us here? Anyone? This is 0 over 0. No one? Class? All right. So we need to multiply by the conjugate, which means this negative becomes positive. And what happens is that each piece of square root comes out. And the denominator, you keep it as a product. Remember uh, when we deal with 0 over 0, the problem is not 0 in the numerator, the problem is the 0 in the denominator. So we are hoping that h goes away and we just keep it as a product. Notice if you do the math, over here you have 3x plus 3h plus 1 minus 3x minus 1. So everything cancels out, and the only thing left is 3h. I hope you see that. Everything cancels out. 3x, negative 3x, positive 1, negative 1. And you factor out the h, and when you factor out the h, before even we go there, when you factor out the h and you drop it, you're practically done. Now let's replace the h with 0. And when you do that, the first radical becomes the same as the second radical. So the denominator has two of them, 3 over 2 square root of 3x plus 1, and it is called f prime of x. F prime of x. Pretty straightforward, class. Now, what happens next? It's very simple. You need two things to come up with the equation of a line. You need the slope and you need a pair. Okay, so this is f prime of x. What is the slope? The moment you fix the x at any specific number becomes the slope at that point. So replace the x with 8. 3 times 8 is 24 plus 1 is 25, comes out as 5, 3 over 10. So that's your slope. Now, remember what I told you, we could have just the x. What about the pair? Plug it in. 3 times x, 3 times 8 is 24 and 1 is 5. It comes out as 5. So we have the pair, we have the slope. And we use the formula y minus y1 equals m times x minus x of 1. Therefore, y minus 5 equals 3 over 10 x minus 8. Now, from here to here, I hope you don't have any problem. I'll quickly give you a hint, at least just to be on the safe side. Y minus 5 equals 3 over 10 times x. Now 3 over 10, when you multiply it by negative 8, you get negative 24 divided by 10, or 12 over 5. We are going to move negative 5 becomes positive 5, which is 25 over 5. And when you add up with negative 12 over 5, gives you positive 13 over 5. Now, one of the things that is important for everybody to notice is that when you have this pair class, this pair belongs to the original function. And it's on that function. Also, it's on this tangent line that we just came up with. So it should satisfy that. And assuming that our slope was correct, if you plug in 8 here, it should give you 5. So when you plug in 8, you get 24 over 10, 12 over 5, and 13 over 5. They do add up to 5. So it does work, and that's important, everybody. Okay. All right, class. So again, a quick synopsis of that. When we are given the function, we need a pair, we plug in 8 and we get the pair. Okay, class? And we plug in, that gives us the pair. We find f prime of x, and now when we plug in, that gives us this slope. We have the pair, we have the slope, we come up with the equation of a line easy. All right. If the graph of a function is given, how do you come up with the graph of f prime of x? So I want to look at this concept quickly. First and foremost, I hope you realize at this point, you have a horizontal tangent line. Same thing here, same thing here, which means at peaks and valleys, local extrema, f prime is 0. On the other hand, over here, I hope you see that f prime, but this is decreasing, f prime is negative, increasing is positive, so on and so forth. So there are three important things to remember, okay? When we have peaks and valleys, local extrema, f prime is 0, f prime is positive when f is increasing, and it's negative when f is decreasing. So what I want to do, I want to quickly show you how I would graph this, and then, of course, you can always have a more detailed information. So what I want to do, I want to go to one node and show you that. All right. So here what is going on, class, we have this point. Okay, now look at the way I have it. Those refer to the fact that we are dealing with a horizontal tangent line, okay? And so if I were to graph this, I would start with easy points. So what are the easy points? This corresponds to 0. This corresponds to 0. So those points corresponds to 0. Okay. Now, let's go with this portion of the graph. This portion of the graph is decreasing. Okay, as you can see, f prime is negative, and therefore that means this is, remember, this is y equals f prime of x. This is the graph, okay? So it's below the x-axis. Now, something like that. If you look at this portion, class, from here to here, okay, this is increasing and f prime is positive. So it has to come back up. But what happens, it has to go back down at some point wherever you see the 0. So from this point, look at this point versus this point. Those 2 points, they give us 0. So it goes up and it has to come back down. When we are looking at this portion of the graph, it's decreasing. F prime is negative. So it goes below the x-axis, but has to come back up, back to 0 class, okay? And then finally, if we are looking at this portion of the graph, okay, it's increasing. That means f prime is positive. That means it has to come back up, okay? Now, of course, I have a better graph here with a little bit more details. So we have this, we have those points, and here's the graph. Pretty much the same graph I went over, class, okay? It's very similar to what we just did. So I hope everybody's comfortable with that. Now, one thing that I want to make a point of is what happens as far as this point is concerned. How do they come up with that? This is a made-up point. Pick a point, for example, x equals 5, and do your best to draw a tangent line. When you do that, you can calculate the slope of that line by just picking up a couple of points carefully. That's what they have done, maybe this point and this point. And then the slope is about 3/2 or 1.5. So you have the pair 5, 3/2 or 5, 1.5 on the graph of f prime of x. You don't have to worry about that. So I'm going to recap. Easy points, A, B, C. Those are easy points. And after that, see whether the function is increasing or decreasing, and there you have it. Let's start with the simplest example we can think of. This is a linear function, as you can see. And if you want f prime of x, you recall that by definition, it is the concept of a slope. So all you have to do, calculate the slope. So if you can calculate the slope for this line, for any line, its derivative has, you calculate the slope. For example, m equals 5, then y equals 5 is the answer. M equals -8, y equals -8 is the answer. So those are the answers. If the line happened to be horizontal, then the slope is 0. The x-axis is the answer. And if it's vertical, it doesn't have any. So you calculate the slope. This one is very obvious. This is 0, 0. This is 1. This point class has coordinates 1, 3. It's important to see that the scale on the y-axis is not the same, and that's fine. And so y equals 3 is the answer. Again, pretty straightforward class. Pretty straightforward. Okay. All right. So for any line, just calculate the slope. Y equals the slope is the answer. All right. Let's look at this one. Now, again, easy points, this one and this one. Okay. Let's just, again, I want to go to OneNote and show you. Okay, so we have this. Okay, so we have this point, and this point. So again, we try our best. So again, corresponding to this point, we have this point. This is not to scale, but you're corresponding to this point, we have this. Okay, so that's the first thing. This is the graph of y, or equals f prime of x. Okay, so with that being the case, let's look at this portion. Okay, so this is increasing, as you can see, and f prime therefore is positive, so it's above the x-axis. I mean, something like that. It doesn't have to be perfect. If you look at if you look at this portion, look at this portion of the graph. This portion is decreasing. F prime is negative. So it has to go below the x-axis. But the reason it has to come back up, because there is another 0, as you can see. So it has to come back up. And finally, this portion of the graph is increasing. F prime is positive, so it has to come back up. So it looks something like that. Okay, class, I hope everybody is comfortable with the concept. Okay, so with that being the case, let's look at the answer here. Okay, so we are looking at those 2 points corresponding to those 2 points, and I've explained the concept of increasing, decreasing, and how we arrive at it. Now, let's look at the last one quickly. Okay, let's look at the last one. Clearly, this corresponds to 0, right? So you have a horizontal tangent line here corresponds to 0. If you look at this portion is what? Increasing, right, class? Increasing. That means what? F prime is positive. That means what? Above the x-axis. This is decreasing. Decreasing. That means F prime is negative. That means below the x-axis. So it looks something like that. So the green one is the answer. And that's a rough sketch. I hope everybody is comfortable with that, okay? Okay. A function fails to be differentiable under the following conditions. If you have a sharp corner, if you have a discontinuity could be a jump or a vertical asymptote. Or if you have a vertical tangent line. Okay. So a corner or a kink, the graph has no tangent line. The idea is that how do you draw the tangent line? Think about this, class. Think about this. Where would you put it? How would you put it? Okay. So that's the idea of a corner. Discontinuity. Okay. If a function is not continuous at a point, it's not differentiable at that point either. Okay. So a jump or a vertical asymptote. For vertical tangent line, what happens is that if you take the derivative of f prime, because remember f prime represents ultimately, if you replace the x with a specific value a, it represents the slope of a tangent line. So this is representing the slope of a tangent line, f prime, f prime. So as x approaches a. If it is approaching infinity, that means you have a vertical tangent line. Remember, what I really want to explain here is that when we discussed lines, we said horizontal line, slope is 0. Then we have lines with a positive slope and a negative slope. And what about the vertical line? We defined the slope as undefined, but the slope is really infinity or negative infinity. That's what we are really saying here. Okay. And so both sides have the same. Now we have a cusp, which is sometimes confusing with the sharp corner or even a vertical tangent. The difference is you still get the same infinity that we had here, but both sides have different. In the case of a vertical tangent line, you have both of them the same, both positive or both negative infinity. In the case of a cusp, one side is infinity, one side is negative infinity. I don't want you to worry about that. It's really not that big of a deal, or at least I don't believe it's that big of a deal. And sometimes I've seen students mixing up a corner with a cusp and a tangent. Vertical tangent line is fine. I will show you the precise difference between a corner and a vertical tangent line, and it becomes obvious. So these are definitions I want you to at least have in the back of your mind. You don't have to worry about it at all. I give you a simple example and it becomes clear. I hope it becomes clear. So having said that, okay, let's look at this case, okay? We want to see how to graph the function, which is the derivative function. Please understand we have 1, 2, 3, 4 line segments. So assume you don't have 4 line segments. Assume you have 4 lines. So just stick with one. Let's assume this is just the line you have. Okay, I want to make sure everybody understands just this one. I hope you see if I had this one, all I had to do calculate the slope for that. Let's say, and I'm making it up. Let's say the slope is equal m equals negative 10. I'm making it up. Then y equals negative 10 is your answer. You're done. You do the same thing for this guy, and this guy. So that's simple, conceptual. Okay. Now, first of all, I give you the points and we'll figure out the slopes in a moment. Okay. Then what I want you to know, what happens at the corner? It's not differentiable. We get a hole, we get a hole, we get a hole, and that's the idea. So first and foremost, let's put those pairs. I'm assuming everybody can calculate this slope by now. 0 minus 1, okay, is negative 1, minus 1, minus 3 is positive 2, is negative 1/2. So the slope is negative 1/2 for this one, which makes this one positive 1/2. This one is 1 and this one is negative 1. So again, I'm assuming you can calculate this in your note. In no time, you are a calculus student. Maybe I quickly put this one down. So for this one, okay, slope is 0 minus 1 and minus 1 minus 3, and that gives you 1/2. Okay, so negative 1/2. So if I wanted to graph this, I would graph the line y equals negative 1/2. So I would suggest you graph the following: y equals negative 1/2, y equals 1, y equals negative 1, y equals 1/2. and then put them together where you must. At the end, there is nothing to put together. They are all sharp corners, therefore not differentiable. So I hope you see, you want to draw those 4 lines and then cut them where you must. And this is what you get. Pay attention to the graph. I hope it makes sense to you. I think it's pretty straightforward, class. Again, calculate the slope. Come up with the equation of a line y equals those, and then take it from there. Okay. The graph of a function is given, where and why the function is not differentiable. So let's start with the first one. I hope you see that what's happening here, we have a discontinuity or a vertical asymptote, so it fails at you. How about here? Well, over here is a vertical tangent line. If you say the cusp or a sharp corner, I'm okay with that. I will discuss the difference in a moment after we're done. So at x equals 0 and at x equals 3. Very straightforward. When we look at this guy, obviously we have a jump, we have a discontinuity at this point, -1. And then we have a sharp corner at this point, 2. Those are the ones that fail. So what do we notice? And that's what I want to discuss. As the difference between a sharp corner and a vertical tangent. Again, if you don't see it, I don't want to dwell on it too much. But here's what happens with the sharp corner. Sharp corner, it's always like a V shape, or maybe a V shape that is upside down. Okay, like this. Okay, V shape. Okay. And so clearly you see a V. Whereas vertical tangent line, ultimately it looks like it's going just up or down, by the way. It could be going down, okay? Clearly it's going up. And so we should be able to tell the difference between the two, I hope. All right, this is the last section. We're gonna practice with, differentiation formulas as far as the limit is concerned, okay, class? And we don't have to worry about that later on, but for now, let's stick with that. Later, we do use that for the proof, and but it's important to be able to use it for this section and the previous section. So take a look at the formula. This one or the same thing, I'll put it here. So just plug in. If you could plug in, practically you're done. That is the only calculus step. So I'm going to put 5 x plus 1, I'm going to put x plus h. So I get the limit as h approaches 0 of 5 times x plus h plus 1 minus 5x plus 1. As long as you can simplify the numerator, practically you're done. So this is what? 5x plus 5h plus 1 minus 5x minus 1. Everything cancels out except 5h. I hope you see that 5x and minus 5x, positive 1 and negative 1 go away. The only thing left, 5h, drop the h. Limit of 5 as h approaches 0 equals 5. Now granted, and some of you know that, this can be done in a split second as of next section. But for now, part B, again, put it into the formula. F prime of x is the limit as h approaches 0 of f of x plus h. What is f of x plus h? 2 over x plus h. Okay. Complex fraction. How do we deal with complex fraction? We multiply by LCD, which is x times x plus h. I hope you're comfortable with algebra, class. So if I multiply the first fraction by it, x plus h goes away, I get 2 times x. The second one, x goes away, minus 2 times x plus h. Now that's pretty straightforward. Now we have 2x minus 2x minus 2h, and the numerator simply becomes negative 2h And when you drop the common factor of h, the top has only -2, the bottom has x times x plus h. You're taking a limit as h approaches 0. Now we are going to put the h equal to 0. That means the parentheses becomes the same as x. So this is x times x, or x squared. And that is your final answer, class. Again, this can be done a lot faster using differentiation formulas coming up. And I know that. We are just practicing with the definition. Here's another one. We are going to put it into this formula again. Okay. As long as we can do that, we are practically done. So 7 times x plus h quantity squared plus 4 minus the parentheses 7x squared plus 4. And I'm sure everybody knows that, but let me just quickly show you that this portion becomes x squared plus 2x h plus h squared. And now you're going to multiply this by 7. Okay, so 7x squared plus 14xh plus 7h squared. And plus 4 minus 7x squared minus 4. And as you can see, almost everything cancels out except these two pieces. What do? We factor out the h. We do factor out the h. And when we do that, h drops. Okay. Let me just write that in case you need to see this. This is, and I'm interested in getting rid of the h. Class, I can factor out the 7h, but let's just take out the h just because I want to get rid of the h. Otherwise, proper factoring, it's not this. Proper factoring is taking out 7h. And now you replace the h with 0, and that's your answer. Pretty straightforward. Okay. All right, class. Now, the next one is the higher derivatives. In short, the higher derivatives means take the derivative again. Okay. Take the derivative again. And when it comes to higher derivatives, normally, class, we do use the formulas and differentiation. I don't want to really waste time on that because it could be just tedious and take a long time. I'm not interested in doing that, but I want to just mention it here, at least we have been exposed to. By the way, speaking of the notation, dy dx is the Leibniz notation, okay? Because Newton and Leibniz were given the credit for inventing calculus, although calculus have been in the process for over 2,500 years. But anyways, they were given the credit. In any event, having said that, so taking d dx, taking the derivative of dy dx gives us, this is the notation we call d2y dx squared, d2y dx squared, and I'm going to read it that way. It simply means the second derivative. And one easy way is f double prime, okay, f double prime, okay. Now, it says f of x, just as an example, is x cubed minus x, find f double prime. So, class, I don't want to go through this 2 times, so I'm going to use the actually next section. I say, assuming you've gone through the process and you find f prime, now how do we find f double prime? I want to go over that and show you that one, okay? Again, remember, when we want f double prime, that means now take a derivative of this one using the definition, the limit, okay? That's what we are going to do. So first and foremost, when we say f double prime, that means take the derivative again. That's the meaning of it, okay? So if you look at the definition that we had, okay, f prime of x, okay, now we can use it here, and instead of f, we are going to put f prime. So think about the concept, okay? Think about the concept and what happens. Remember what we have, class. Just put it up here and remind you. You know this, but for the sake of argument, remember f prime of x, I'm putting it up here. F, what is f prime of x? F prime of x is the limit of f of x plus h minus f of x over h as h approaches 0, right? So now, if you want f double prime class, okay, use it. Okay, so if you want f double prime, okay, so to make this double prime, you make this one f prime. You see that? That's how we arrive at it. So if you want double prime, you want f. So plug in. So plug in x plus h here. Now this is simple. Everybody knows how to do that. And again, remember x plus h squared, we've done that. X squared plus 2xh plus h squared. You multiply it, and as you can see, just about most everything cancels out. 3x squared minus 3x squared. Okay, minus 1 plus 1. You are left with these two. Okay, so let me actually use this. So we are left with these two. Okay, and we can take the h out. Gives us 6x plus 3h. We factor out the h, so we are dropping the h. And as h approaches 0, you get 6x. And by the way, these are the formulas for f prime of x, and f double prime of x, okay? So f of x, f prime of x, and f double prime of x. So this is f of x, this is f prime of x, and this is f double prime, okay? And f double prime is in green, of course, okay? So I hope everybody is comfortable with that. So we have nothing to worry about, okay? We're going to move on to the next. All right, the higher derivatives class, one of the application is dealing with the position function, okay? We have the s of t, okay, as the position function. When we take the derivative, it becomes the velocity function. If we take the derivative again, it becomes the acceleration. So that's one application of that. We will look at that later on when we are dealing with differentiation formulas, because I really don't want to use class. I don't want to use this, what do you call it? Definition to do the work. Not that it's not doable, it's just that I don't want to take that much time to do it, okay? In any event, let's look at the next page. So this is, by the way, again, avoid triple prime or and so forth. You can keep on, differentiating and doing the math. It's really not that big of a deal. And so in any event, we have this. Let's just move on to the, all right. Where is this function differentiable? And class, basically, you can just go through the process to find out what happens, okay? And that's what we are going to do. So if the function is given as absolute value of x, okay, remember by definition, it's equal to x if x is larger than 0, and it's equal to negative x otherwise, okay? And not larger than or equal to 0, okay? Everybody remembers that. So let's go with absolute value of x is equal to x, okay? And so let's see what happens as far as the definition. So f prime of x is the limit of this function, okay, as h approaches 0, okay? Now, this is the general formula, okay? Now, what happens if absolute value of, if x is larger than 0 class, if x is larger than 0, and when h approaches 0, then x plus h is always larger than 0 for a simple case, because h is minute, h is approaching 0. And so that's why it's important to see that absolute value of x plus h is the same as x plus h if x is positive. Okay. The reason why, because h is extremely small, so it has no effect. And so it becomes this and this, and the answer is 1. So f prime of x is always 1 if x is larger than 0. Same thing happens if absolute value of x, if x is less than 0, absolute value becomes negative. And x plus h also, remember h again, it's like 0.0000000000001, meaning h is almost 0 class and it has no bearing. Okay, so you replace it and you see that the answer is negative. So what are we getting at? This function is, if so far, is differentiable everywhere where x is positive or where x is negative. If x is positive, the answer is 1. If it's negative, the answer is negative. So not a big deal. Very straightforward. Okay. Now, what happens is that when we are at 0, we want to see what happens. So that's important. Now, we are looking at actually this one, and we are thinking specifically at x equals 0, absolute value becomes 0. So look at that one. So we are going to replace it with a 0, okay? And you get 0 plus h minus absolute value of 0. This goes to 0, and this is absolute value of h. So the answer is this. Okay, so I want to make sure everybody understands f prime of 0 is this. Okay, the limit of absolute value of h over h as h approaches 0. Now, what happens if we approach 0? Okay, h approaches 0 from the right. If it's 0 from the right, you can drop the absolute value and it becomes 1. If we approach 0 from the left, we can drop the absolute value, but we change it to minus h, and it becomes negative 1. Therefore, what does it mean? This function, f of x equals absolute value of x, is differentiable everywhere except at 0. Why not? Because f prime of 0 from the left and right are two different things. So f prime does not exist. F prime of 0 does not exist. And that's extremely important for everybody to see. And therefore, we have the following. F prime of x is always 1 when x is positive, always negative 1 when x is negative, and doesn't exist at 0. So if you look at the graph of your function absolute value of x, by the way, let me just look at the absolute value of x, okay? The absolute value of x, you know it's a V shape. So this one is a line segment. So the slope is the answer. M equals 1. This one, the slope is the answer. M equals negative 1. What about this guy? Sharp corner, not differentiable. Okay, so here's the theorem. If f is differentiable at a, f is continuous at a. The converse is false. That is, there are functions that are continuous but not necessarily differentiable. I hope everybody understands the meaning of this. Okay, I can't really emphasize this enough. Okay. All right, class, we are looking at section 3.1, derivatives of polynomials and exponential functions. In this section, in this chapter, we'll deal with the differential rules. And so derivatives of polynomials and exponential functions, the product and the quotient rules, derivatives of trig functions, the chain rule, implicit differentiation, derivatives of log functions, rates of change in the natural and social sciences, that means applications, exponential growth and decay application, related rates applications, linear approximation and differentials applications, hyperbolic functions. Okay, so again, we recall this one, And basically the idea behind this is understanding the general formula for differentiation, okay, um, and the definition. What we are going to do, we are going to look at differentiation formulas such as polynomials and exponential functions. So those are easy. Let's just quickly discuss. Let's start with a couple of easy ones. We will look at proofs, and then we will look at a couple of examples, see how fast we can use this. If you're looking at the horizontal line, you already know y equals a constant is a formula. You already know the slope is 0, and therefore f prime is 0. So you can look at it from the point of view of a graph. Also, if you look at it from the point of view of the definition, I want you to pay attention to the definition, class. Okay, so here's what we have. Here's the definition. Okay, plug in. Now remember, your function is c. So when you plug in x plus h into c, it doesn't change, it's c. F of x, the same thing, c. So I hope you realize when you have a constant function, it doesn't matter what your variable is, x or x plus h makes no difference. And so with that being the case, the numerator is 0. It's important to know, although h is approaching 0, but it's not equal to 0. But the numerator is 0, and therefore you're dealing with the limit of 0, and the answer is 0. Now, there are other things, so the derivative of a constant is 0. By that, we mean a number. The derivative of y equals 7 is 0, or y equals 10 equals 0, and so on and so forth. You remember this formula from algebra, okay? And we did the following, if we let n over r be m, okay? Then r over n becomes 1 over m. N is r times m, so we can replace the n with r times m. We write it this way. I'm just reminding you what we have seen in algebra. Okay, so p times 1 plus 1 over m to the power of m to the power of rt. Now this thing, when you let m go to infinity, if you recall, we had a equals p e to the power of rt. I'm showing you the definition of E from algebra. I hope you remember that this is from algebra. Where E is just like pi, it's an irrational number. It's 2.71828, and it continues indefinitely. So this was reminding you of what you have seen. This one, however, we will go over it, okay, class? So this one, by the way, this I just changed the m to n because of different text. Sometimes they use m, they use n, sometimes they use h. Okay. Now this one is new, and we will look at it in this section. So there are two definitions of E. One of them is the limit of 1 plus 1 over n to the power of n as n approaches infinity. And the other one is the limit of e to the power of h minus 1 over h as h approaches 0. This one, we prove it. This one was proved in algebra. I just reminded you. Okay. So I hope everybody is okay with that. So having said that, some formulas that are pretty straightforward, class, let's just quickly discuss them. The derivative of x is 1. This is called the power rule. The derivative of x to the power of n is n to the n x to the power of n minus 1. I'm going to look at the proof for that. The constant multiple, if you have a constant and times a function, you can take it out. If you have a couple of functions and you're differentiating, separate. As addition and subtraction makes no difference, okay? And here's some more formulas. Okay, let's quickly recap, and we will look at the proof later on, okay, class? The derivative of a constant is 0, x to the power of n is n, x to the power of n minus 1. E to the power of x is itself, sine gives you cosine, cosine gives you negative sine, tan gives you secant squared, cotangent negative cosecant squared, so on and so forth. Secant is secant. You don't have to worry about any of this. You need to know this for this section, this one, and this one. So we are concerned with the first three, and we already proved the first one. we are going to prove the second one. So take a look. Let's look at the derivative of x to the power of n, and we are looking at it from the point of view of binomial distribution. We're going to prove that. So simply put, plug in x plus h. Okay, class? So if you plug in x plus h, this is what you get. I hope everybody is comfortable with that. Now, how do we expand that? Okay, just you remember, for example, x plus h squared, x plus h cubed, so on and so forth. Okay, so the formula is as follows. So I'm going to remind you what you have seen, okay, before. I'm going to show you in one more. Let me see, maybe, do I have room here? Okay, class, what we learned in algebra, okay, was the following. If we had a plus b to the power of n, it was cn0 e to the power of n, and cn0 becomes 1. This is a combination. I will write the combination in a moment. cn1 a to the power of n minus 1b. And I'm going to put to the power of 1, although I don't have to, just to make a point, they add up to n, their exponents. cn2 a to the power of n minus 2b squared, and all the way to the last one, cnn a to the power of 0, b to the power of n. So simply put, use a different color. This becomes 1, and this becomes a to the power of n. And this becomes 1, and this whole thing becomes b to the power of n. I hope you remember that. This was called binomial theorem. You can look it up. It's in your algebra book. Binomial theorem, okay, when you want to expand it. Okay. And so what happens is that when you look at this one, for example, this becomes n, okay, class, this becomes n. And cn2 becomes this one. And the formula for the combination cnr is n factorial over r factorial times n minus r factorial. I hope you remember these formulas. You're not going to use them. I'm just refreshing your memory. So notice what happens. You expand this, and now that you have expanded it, x to the power of n and minus x to the power of n cancel each other. So you can write the rest of it. Okay. Now notice what happens to all of this. Okay. All of this have an h. I hope you see that. This has an h, but this has h squared. And the rest of them have the same thing, but higher power. So when you factor out the h drops from the first one, but the next items, they do have them. So take a look at what happens next, class. Again, this first one, h drops. This next one, h squared changes to h because we are dividing by h. This one, h to the power of n minus 1 becomes n minus 2. This becomes the power of n minus 1. All of them have h. All of them go to 0 with the exception of the first one. And that's the answer, believe it or not. I hope you realize what we are doing here. It's pretty straightforward and it's very simple, class. Again, I'm not going to expect you to do the proof for me. Pay attention. I'm not asking you to do the proof for me. But what I'm asking, if you could follow it, it will help you understand the concept better. And I really can't emphasize this enough. Okay, class? So I hope you are comfortable with that. Okay? So having said that, let's go to another proof. When we have f plus g and we differentiate, it's the same as differentiating one by one. So that means the derivative of the sum is the sum of the derivatives. Okay, class? Again, just there are many proofs like this. We're going to look at a couple of examples just so we are exposed to it. At least we can say we've seen it once. If we come across it again, we won't be scared of that. Okay. Here's the process. We let capital F of x represent this, and we're going to put it in here. And we're going to write capital F prime is the limit of capital F x plus h by capital F of x over h. Now we are going to replace this with this and this. So this becomes F of x plus h plus g of x plus h, and the rest is pretty obvious. Okay, so I hope everybody's okay with that. We are simply doing the basic step involved in algebra. And so having said that, what do we do next? We just put this part with minus f of x and this part with minus g of x. I hope you see what happens. This negative gives us minus f of x minus g of x. So this is minus f of x minus g of x. That's what it is, okay? And so with that being the case, if we put together this one and minus f of x gives us this, and this one gives us this one. So I'm going to separate them into two pieces, and it's f prime plus g prime. This is a very simple proof class. I hope everybody is comfortable with that, and nobody has any problem with it. However, as I mentioned, let's actually use this. Let's use these differentiation formulas and not to worry about the proof so much. Okay, let's see if we can do that.